All right, so today we're going to talk about molarity, and molarity has the letter capital M, so please be careful with that. Lowercase m we know is mass sometimes. It's also meter, so big M means molarity. And molarity has the equation of moles of our solute. Remember, solute is the thing going into the solution that is in a lesser quantity over liters of the whole solution, and the solution is the solute and the solvent together. So for example, if we have sugar going into hot tea, our sugar is our solute, our hot tea water is our solvent, and the mass of both of those together would be the solution. So again, we usually just abbreviate this as molarity, big M, equals moles over liters. All right, so liters, not milliliters. Now you can go ahead and read through how to make a solution. Knowing the steps is very important. One thing I do want to point out is when we make a solution accurately in chemistry, we have to use a volumetric flask. And this volumetric flask is expensive because they are hand calibrated for a certain singular volume. And we usually use 100 mils or 250, 200, sometimes 1,000. And if you were to look closely, you can ask me next time in lab, there is an etched line on these. And that etched line, if when you hit the meniscus on there, means it is the most accurate way to measure a liquid in chemistry. And so make sure you read through these steps. So again, molarity, big M, moles over liters. Let's go ahead and try an example. So again, our equation for molarity we know is moles over liters, and we have to be able to utilize that because we are oftentimes given the amount that we need to weigh in grams. Obviously, we don't have a scale that can measure moles, but we have grams. So we're given 75 grams of H2SO4. And so before I can even go ahead and calculate the molarity for this, I have to put this into moles. And to do that, we know we're going to use the molar mass. So calculating the molar mass of H2SO4 gets you 98.08. I went ahead and did that. I divided and got 0.765. I like to keep three significant figures to match the 75 grams provided. Now, I want to go ahead and divide that so that I can divide by the liters, but the problem is this 500 milliliters is in, of course, milliliters. So before I can do that final division to get the molarity, I have to convert to liters. Please, please, please do the calculation because this is the biggest mistake. Students will get really far in this chapter and then convert from milliliters to liters incorrectly every day. So if you are having trouble with that, please write out the equation. Liters are going to be smaller than milliliters, and you can see the equation here. So once we've solved for moles in liters, we can go ahead and do the final division to solve for our molarity, and then we want to make sure that we end with big M. Now another way you can write the unit actually is MOL over liter, okay, or moles per 1 liter, any of those, but big M is traditionally what we see. Again, little m will not get you the correct unit point. That is not molarity, and just moles will also not get you the unit point. So make sure you're either doing big M or moles over liters. So we have one more example here going the opposite way. We have a molarity and we're trying to figure out how many grams of something we're supposed to weigh to create the solution. So what I have to do first is solve for moles because the only thing you can get grams from is moles. So I'm going to go ahead and use my equation molarity equals moles over liters. Put my molarity in, put my milliliters into liters, which I showed you how to do in the previous slide, and then go ahead and multiply both sides to get that out of the denominator. And then when I end up with my amount of moles, I can go ahead and use molar mass again for NaCl, table salt. I can multiply and get 4.50 grams of NaCl. So just to review how you'd create a solution, you would weigh out your 4.50 grams of the NaCl using a balance. You'd go ahead and put it into some sort of volumetric flask, most likely a 500 mil, and you would put enough water for it to dissolve, and then you would go ahead and once the solid is dissolved, you'd fill it up to the meniscus hitting that etched line, and then you would invert 10 times, okay? And therefore, you would have the most accurate 0.154 molarity solution of NaCl. Now we're going to go ahead and look at dilution. Dilution is when you have something that's more concentrated and you're adding water to make it less concentrated. And so water is our typical solvent. It will be our typical solvent in Gen Chem. We call it the universal solvent, And so you may see the equation two different ways. Your textbook writes MIVI, which the I stand for initial, and then MFVF, F meaning final. I prefer to write it as M1V1 equals M2V2. And again, the initial is usually the 1 and the final is usually the 2, but again, either one of those is fine. A couple things I want to point out about this equation. These are being multiplied, so make sure you know that. Big M is molarity, not moles. Not moles, it is molarity. And V is volume. Now, the units for volume, it doesn't matter if they're both liters or both milliliters, as long as they're the same thing, because they'd cancel out. So unlike the molarity equation, dilution just has to be molarity, but the units for volume can either be, it actually could be anything, but typically it is liters or milliliters. So we use a volumetric flask as well to dilute a solution. Again, that's just the most accurate way to measure a certain volume. The limitation with that is you only have a certain set number of volumes, so you usually have to dilute stuff in 100, 200, 250, or 1,000 mil volumetric flasks. But it's easy enough to calculate it, and you can always dilute it down from there. Let's go ahead and do an example here. We have a saturated stock. So in case you don't know, that term stock usually means the original solution container. So a saturated just means that it is completely dissolved in there. So a saturated stock of NaCl is 6 molarity. So that's a pretty strong stock solution. And we're trying to figure out the concentration when we take 135 mils of this out and put it into a 500. Now, when students are starting to learn about this, I like to almost draw pictures to help us visualize what's going on, and I'm a pretty good artist, so this should be able to really help you understand. So we have a 6 molar solution, and we are going to take out 135 milliliters of it. So when in doubt, draw a picture for dilution problems, and we're going to go ahead and put it into a new, these are my rendition of volumetric flasks here. We're going to go ahead and put this into a 500 mil. So 135 mils are going to go in there. And again, we're trying to find our new molarity. So I'm going to put an M2 with a question mark, or an MF if you like that. So this helps you just visualize how much is going in, how much is being taken out. And then the concentrated stock is this one. And then we call this one the diluted stock. Okay. So it always kind of helps you kind of fill in these M1V1, M2V2 equations. So let's go ahead and fill in what we know. So we have a initial concentration of 6 molarity. Please make sure you put the units in this equation. It just helps you make sure that you're doing this correctly. And this V1 is how much you're taking out, not the total volume. How much you're taking out of your concentrated stock. So please make sure you write that down if you've never done this equation before. It's not the total volume. It is how much you're taking out of that concentrated. And then my molarity 2 is what the concentration is going to be. And then my V2, this is different. So again, please write this down. This is your total volume of your diluted stock. Total volume, okay, after it's all filled up with the water. So in this case, it is the 500 milliliters, okay? So those V1 and V2 are easily mistaken. Now go ahead and do the calculation. 6 times 135 divided by 100, and you can get your molarity for the diluted stock. In this case, it's 1.62. A good check is that your M2 is always going to be less than your M1, and your V2 is always going to be less than your V1. No, excuse me, your V1 is always going to be less than your V2 because you can't put more in than you already have. So it's always good to just ask yourself that common question, does this make sense? So let's go ahead and do one more example here. So we have a stock solution. Again, stock means usually the concentrated. The HCl is 3 molar or 3 molarity, and we want to create 1.25 molarity, 750 mils of it. So let's go ahead. Why don't you pause the video and try this calculation on your own, and then you can check your answer with me. So I know that my initial stock concentration is 3 molarity, and my initial volume is what I'm looking for. So I'm going to leave that as V. You can make that an X, but I usually like to keep it so that I remember what I'm looking for. And 1.25 molarity and 750 milliliters. So when I go ahead and calculate that, my V1 ends up being 312.6 12.5 milliliters. And again, let's just remind ourselves what that even means. That means to create this solution, I need to take out 312.5 milliliters of this concentrated stock and put it into a solution that is large enough to fit 750 milliliters. And when I fill that up to 750 milliliters, including the concentrated and the water, I will have a 1.25 molar solution. Now, I like this second question because it really helps to clarify what is going on here. You will see this question on a test, hint, hint. Determine the approximate amount of water. So to do that, you need to figure out that if your total volume here is 750, and again, could help you to draw a picture, a volumetric flask. So 750 total, you are putting in 312.5 of the stock, and then the rest will be diluted with water. So if you just subtract those values, you can figure out how much water you have. So 437.5 milliliters. Now, in a problem, it's easy enough to calculate that, but remember, if we were doing this in real life, we would actually just fill it up to the meniscus line, which is more accurate than weighing out 437.5 mils